Hi, so for today we're going to talk about electric flux and Gauss's law. And basically this is gonna be a 1 hour discussion or less. So what is electric flux and what is Gauss's law all about? So let's start. Let's start with defining the electric flux. So if you haven't watched my videos all about electric field and electric charges, you better watch it first before you watch this because there are concepts applied here based on the previous topics, which are the electric fields and the basic electric charges or electrostatic forces. Okay, so let's start. What is an electric flux? So consider that there is a uniform electric field. Okay, there is a uniform electric field represented by arrows here, okay, with the direction going to the right, and it is passing through a certain plane, which has an area of A. Okay, the field lines or the electric field lines penetrate a rectangle surface area A whose plane is oriented perpendicular to the field, meaning the electric field is what? Is perpendicular to the orientation of the plane. Okay, so in this case, we can define electric flux as basically the product of the electric field and the area through which it passes. So, in other words, we have the electric flux as the product of the electric field multiplied by the area through it which passes. Okay? And electric flux is actually represented by a Greek alphabet phi. Okay? So, this product of the magnitude of the electric field, okay, and surface area is what we call the electric flux. And that is basically represented by the Greek alphabet phi with sub E to denote that this is electric flux, because there is also what we call the magnetic flux, and it is different from electric flux. So anyway, we now know that the electric flux again is the product of the magnitude of the electric field E and the surface area A, and that is what we call the electric flux. Okay? More specifically, okay, electric flux is proportional to the number of electric field lines penetrating some surface. So, if we have a larger magnitude, as you can see here, a larger magnitude of electric field, we would be producing a larger magnitude of electric flux or the electric flux itself. And if both the magnitude of electric field is increased and both the area through which the electric flux passes through increase also, we are increasing the electric flux because it is directly proportional both to the electric field, magnitude of the electric field, and the area through it which passes. Okay, if the surface under consideration is not perpendicular to the field, we use the formula more specifically that electric flux is equal to the magnitude, the product of the magnitude of electric field and the area through it passes, okay, times the cosine of theta. And again, we're going to write it down, okay? So electric flux now will become, more specifically, electric flux is the product of the magnitude of the electric field times the area through it passes, then cosine of theta. What is cosine theta here? Or what is theta here? Theta here is actually the angle between the electric field vector, okay, and what we call the normal vector or the area vector. So what is this normal vector or the area vector? For example, we have a plane that looks like this. Okay? So, area vector or the normal vector is defined as the vector which is always perpendicular to the surface. So in this case, we have a plane here that has an area A, okay? And the normal vector or the area vector of this plane is going upward because what? Because this vector, normal vector or the area vector must be what? Perpendicular to the surface of the plane. So for example, if you have this kind of plane from our example a while ago, okay, the surface of the plane is actually facing to the right. So the area vector or the normal vector is in this direction such that it is perpendicular to the surface of the plane. So we can label this as the normal vector or the area vector. Okay? So technically speaking, area is not a vector but it's scalar. But since we are talking about normal vectors here and area vector or area, we can consider this as a vector sometimes. Okay? So what are we going to do here is, did you get what is the meaning of the normal vector? It is always perpendicular to the surface of the plane. So that is the definition of the normal vector. So going back to our image here, to our lesson here, as you can see in the first image, this plate is actually oriented such that it is facing to the right. Okay, so where is the normal vector of this plate? That's correct. It is actually the same as the direction of the electric field. So, if the normal vector of this plane is also in this direction of the same direction as the electric field, then theta, we define theta as the angle between the electric field vector and the normal vector. So, what happens is, in our example, for example, this is our electric field, okay, constant electric field. Let me just redraw this more nicely. Okay, so we're going to try to draw a nice illustration of this. Okay, so this is our plane through which the electric field is passing through. So we can say that this is the normal vector because it is perpendicular to the surface or the face of the plane. So this is the normal vector or area vector. Okay, so let's say that we have also an electric field passing through this from here to here. Okay, just like our example a while ago. So we can label this as the electric field. So if that is the electric field, theta is defined as the angle between the electric field and the normal vector. So what is now the angle of the electric field and the normal vector in this example? Or in this example? Okay, that's correct. The angle is 0. But if you're going to calculate it, EA cosine 0 is simply 1. So our formula here reduces to simply the magnitude of the electric field multiplied by the area. Okay? So, what if the surface is not oriented perpendicularly? So, in this case, as you can see here, we have a surface here. Here is the surface. And the electric field through it which passes is still on this direction. Okay? As you can see, at this point, okay, if this is the plane, the normal vector must be this. That is perpendicular to the plane. Okay? Such that when we are going to measure the angle, that is not 0 degrees anymore. That this theta is now in between 0 to 90. So, if such cases happen, we're going to use this formula, EA cosine of theta. The normal vector is in this direction, the electric field in this direction, so that it creates an angle theta between the electric field and the normal vector. So we're going to use this formula. Okay, so let's consider the three different cases of electric flux. Okay, so in this case, we have three plates that are oriented at a certain angle. And we're going to see what is the electric flux through this. Electric flux through this tilted with a certain P angle. Okay, we can replace this as simply theta angle or with the 90 degrees. So as you can see, we can derive the concept from the equation. So let's say condition 1, okay? Condition 1, EA cosine of theta. Condition 1, let's say that your theta is 0 degrees. Okay, what will happen to the flux? That's the question. So, what will happen to the flux if the angle between the electric field and the normal vector area is 0? Then cosine of 0 is simply 1. So, let's say that we have 1 Newton per coulomb of electric field and 1 square meter of 1 square meter or meter squared of an area. So multiplying that, we have a flux that is 1 Newton meter squared per coulomb. By the way, the unit of electric flux is Newton meter squared per coulomb. Okay, let's say that's the case when angle theta is 0 degrees. Okay, and let's see what will happen. Okay, for case number 2, if we have a theta that is 90 degrees. Plugging it into our formula, okay, again, that this is electric flux 1, this is electric flux 2 in condition 2. So that is must be 1 Newton per coulomb times 1 meter squared. Then we multiply it by the cosine of 90 degrees. And cosine of 90 degrees, whether you like it or not, is 0. And 0 times 1 is simply 0. Okay, 0 Newton meter squared per coulomb. So in other words, if theta is 90 degrees, then the electric flux is always 0. Remember that. Okay, and again, theta is the angle between the electric field and the normal vector or the area vector. Okay, so 0 Newton meter squared per coulomb. So what will happen if in case 3, we have a theta, let's say, between 0 and 90, let's say that is 30 degrees. So, again, for our flux, electric flux, I'm sorry, this should be angle, theta, not phi. Angle 30 degrees. So, again, still the same. For example, we have a 1 Newton per coulomb of electric field. Then we have 1 meter squared of area. And then we have cosine of 30 degrees. So, cosine of 30 degrees, okay, that's equivalent to square root of 3 over 2 or 0.86. So, we have 1 Newton per coulomb multiplied by 1 meter squared multiplied by 0.86. So, what will happen? We have now a flux equal to 0.86 Newton meter squared per coulomb. And as you can see here, class, that we have 3 cases here. If angle is 0, then we have a maximum electric flux. So as you can see, among the 3, the maximum value is when the angle theta is 0 degrees. And that is given by this electric flux of 1 Newton meter squared per coulomb. But if the angle is 90 degrees, automatically the electric flux is 0 Newton meter squared per coulomb. So this is the minimum value of flux you can get, 0. Okay, this is the maximum when theta is 0. Okay, and here we can see the third case, 0.86 Newton meter squared per coulomb of electric flux, and that is because our angle now is between 0 to 90. We have what? 0.86, which is this value is what? Is less than the maximum of 1 Newton meter squared per coulomb, but more than 0. Okay? So this is less than maximum of 1, but more than minimum of 0. And we have the other case, okay, for number 4. Number 4, if theta is greater than 90, let's say our theta now becomes 120 degrees. So what will happen to the flux? Electric flux now would be 1 Newton per coulomb multiplied by 1 meter squared cosine of 120. And cosine above 90 degrees should give you what? A negative value. So cosine 120 is simply 1 times 1. Cosine of 120 is negative 0.5. So now we have a negative 0.5 Newton meter squared per coulomb. So we have now a negative flux. We have a negative flux because flux is a scalar quantity, not a vector. So, fourth case, if the angle is greater than 90, then we have a negative flux. Okay, so I hope you understand that. So, going back to our figure here, it basically wraps up what I've said for the first case. Here, we have a plane here. And the normal vector is also in this direction. The electric field is in the same direction as the normal vector because this plane faces to the right. So it has a normal vector here and the electric field is passing through here also parallel to the normal vector. So now we have an angle which is 0. So we can say that the electric flux here is actually at its, yes, that's correct. If theta is 0, that is at maximum. So the flux through the surface of fixed area has a maximum value when the surface is perpendicular to the field or when theta is 0 degrees. How about in this? So we can expect that this plane is oriented with an angle theta. Okay? So we can expect that the normal vector is in this direction. Well, of course, that is always perpendicular to the surface of the plane. And the electric field is the same direction such that it creates an angle theta of less than 90 degrees but more than 0 degrees. So what do we expect? If the theta is less than 90 degrees but more than 0 degrees, we have an electric flux that is less than the maximum, right? The maximum value, but more than the minimum if the surface is tilted with some angle between 0 to 90 degrees. Okay, so how about the third one? Okay, it is very evident that the area vector is this, such that it is perpendicular to the surface of this plane. So, and the electric field vector is in this direction. So, in other words, the angle between the electric field, okay, denoted by these lines, parallel lines or horizontal lines in the x-axis, and we have a normal vector here. The angle between them or the theta between them is 90 degrees, such that if we're going to enter it in our calculator to calculate the flux through the plane, this should be 0 because cosine 90 degrees is 0. So the flux is 0 when the surface is parallel to the field. And I hope you understand the basic concept of electric flux. And again, the formulas are important in determining the relationships or understanding the concept of electric flux. So, how about if the flux is concentrated in a non-uniform electric field? Or if the electric field is not uniform but varies from point to point over the area A. Or, for example, we have this kind of shape. Okay, we have this kind of shape. You can hypothesize, sir, that the electric field, for example, we have an electric field passing in this area. Okay, so this is the electric field. Okay, let's imagine that we have a couple of electric fields passing through this surface. Okay, we can say that since this is a 3D surface, that the electric field here, taken here, we have electric field and a normal vector here, is not the same as the electric field vector here. Why? Because the normal vector here is not the same as here. And it's also not the same as here, not the same as here, not the same as here. So, we have different flux. Okay? So, what are we going to do? According to our problem, okay, or according to our lesson or our guide, he actually what? He or she actually divided this surface into a small area such that delta A, okay, such that this has a normal vector, this has a normal vector, another a normal vector here, passing to the electric field. So what are we going to do is we divide this air surface into a very small surface, delta area. Okay, in a very small area. So what will happen after we divide it? We calculate all the electric flux because as what I have said, the electric flux throughout here is not the same because the shape are not uniform and therefore we have a non-uniform electric field. So what are we going to do is simply what? We get here the electric field E sub I, that's one component of the electric field, and we have delta A sub I, which is one component of a surface area, and we have theta, and that is the theta, and we can get the electric flux at this certain point only. But how about if we're going to get all? So we're going to sum up all the products of the electric field and the delta A. Okay? So what are we going to do? The delta electric flux. So what are we going to get here is also a delta electric flux. So that is not the electric flux of the whole system, of the whole surface. So we have the formula here. Okay? We don't have any new formula here. Simply, we have a subscript of I to denote that this is a piece of area and a piece of electric field passing through this surface. So we have E sub I times delta A sub I cosine theta sub I. Okay? And we can actually, this electric flux is from the dot product. Actually, the definition of electric flux is basically electric field vector dotted by the area vector or the normal vector. So that we have here these vectors. Okay, so after that, in order to get all of the flux, okay, that is approximately equal to the summation of all the dot product of electric field sub I and the delta A sub I. Meaning we have a piece of A sub I and delta E sub I here. We have another one here, we have another one here, we have another one here, another one here, and so on and so forth until we get the summation. We can get the approximate electric flux. I hope you get what I'm trying to say. So we get the approximate summation of the electric flux. But okay, in order for us to really get the accurate electric flux of this surface, a more popular operation is to use the integral. Okay, so basically, if the number of areas element approaches zero, then the number of elements approaches infinity and the sum is replaced by an integral sign. So that we can cover all, because integral is actually has something to do with finding the area of this surface. So if we can get the area by dividing it into infinite small area, okay, we can use the integral. And by the way, electric flux, another definition of electric flux or formula for electric flux is simply, okay, if you have a non-uniform electric field, is simply the integral of the dot product of the electric field vector multiplied by differential area vector or the normal differential normal vector. So we have the definition of flux. This is still the same, the dot product. Okay? So we have now an integral here. Okay. So that's worth memorizing our formula. So flux through a closed surface. So a closed surface is defined as the surface that divides space into an inside and outside region so that one cannot move from one region to the other without crossing the surface. So for example, we have a closed surface here. Okay, we have a closed surface here, and it is subjected to a uniform electric field here. Okay, we have an electric field here. So we have a flux. Why? Because this closed surface has its own normal vectors. Okay, so and at different points of this closed surface, we can find that the flux are different also. So for example, we have here in number one, okay, number one here, we have here have this image enlarged. So if this is now the plane, we have now an electric field vector in this direction, and the normal vector is in this direction. We can see that the theta is less than 90 degrees but more than 0 degrees. What do we expect for this flux, for this certain of flux? What can we say? That the flux is positive. Okay, the flux is positive in this first image. And if you're going to look at this segment of the closed surface, you get a segment, you get a plane here, okay, a small plane here. The area vector is in this direction and the electric field is in this direction. So the angle between the area vector and the electric field vector is 90 degrees. So what do we expect at the flux here? Yes, that's correct. That should be 0. Okay? So, and again, in this portion, number 3, we enlarge this plane, okay, such that we have now a normal vector in this direction, okay, and the electric field is still in this direction. As you can see, the angle is greater than 90 degrees. So, what do we expect? That the flux here at number 3 is equal to a negative value. That's what I've told you a while ago. Okay, so we have the meaning of net flux. The net number or the net flux is defined as the proportional to the net numbers of lines leaving the surface. Oh, I'm sorry. Net flux is the number of lines leaving the surface minus the number of lines entering the surface. So we can have a negative electric flux or negative net electric flux. So as I've said a while ago, getting a negative flux is okay. It only means that the number of lines leaving the surface must be what? Less than the number of lines entering the surface. So we have a negative line. So therefore, if more lines, here's what I'm trying to say, if more lines are leaving than entering, based on this definition of net flux, the net flux is positive. Okay? If more lines, electric field lines, are entering than leaving, then the net flux is negative. Here we have, again, the formula, and the integral with the closed circle here only means the closed surface integral. Okay? So, let's try to solve some problems here. I prepared some problems here. Okay? So this is the same as our on the PowerPoint presentation. A disk with a radius 0.1 meter is oriented with its normal unit vector n at an angle 30 degrees to a uniform electric field E with magnitude 2 times 10 raised to 3 Newton per coulomb. So letter A, what is the electric flux through the disk? So as you can remember, class, we have a drawing here, an illustration here, an image here. We have a disk. Okay, we have a disk here, and the electric field vector is in this direction to the right. Okay, uniform electric field vector, and we can notice that the normal vector is this. Okay, because it is always perpendicular to the surface of the disk, such that it creates an angle of 30 degrees between the electric field and the normal vector. So what is the flux to the disk? So if we are going to compute the electric flux, simply EA cosine of theta. Okay? And we have the magnitude of electric field given here as 2.0 times 10 raised to 3 Newton per coulomb multiplied by the area. What is this area? Again, the area, the surface area. Okay? So the surface area through which the electric field passes. And the surface area of this disk is simply a circle. Okay? So if this is a circle, we have a radius of 0.1. So the area of circle is pi r squared, 0.1 meter squared. So that's our pi r squared. Cosine of the angle between the electric field vector and the normal vector, that is 30 degrees. Okay? Upon computing, our electric flux should be cosine 30. So we have 54.41. So our electric flux is computed as 54.41 Newton. Again, the unit is Newton meter squared per coulomb. So that is the flux through the disk. Okay. Okay. So for letter B, okay, it says, what is the flux? What is the flux through the disk if it is turned so that it's normal? Okay, it's normal, meaning to say the normal vector is perpendicular to electric field vector E. What do you think is the answer? If the electric field is perpendicular to the normal vector, then we have a theta of 90. And cosine 90 is simply 0. If the cosine or if the theta is 0, then our electric flux should be what? 0. Okay? If the theta is 90, well, that's what I meant. If the theta is 90, cosine 90 will be 0. Okay? So our answer for letter B is 0. Okay? Letter C. So for letter C, what is the flux through the disk if it's normal is parallel to electric field E? So here's the problem. If the electric field is parallel to the normal vector, the angle between them should be 0. And we're going to calculate the flux. Okay? Still the same formula. If they are parallel, if electric field is parallel with the normal vector, then their angle is 0. And cosine 0 is simply 1. So our formula is now reduced to EA. Okay? And our electric field is 2 times 10 raised to 3 Newton per coulomb multiplied by the surface area of this disk, pi 0.1 meter squared. So what do we expect? What answer do we expect here in letter C? That the answer here in letter C should be greater than the 0 and 54.41 because the theta is 0. Okay, so let's try. 2 times 10 raised to 3 times pi times 0.1 squared. Okay, our answer should be 62.83. 62.83 Newton meter squared per coulomb. So this will now be our answer. Okay, understand? So let's continue our discussion for problem number 2. Okay, so here is our answer, by the way. So problem number 2 is to consider a uniform electric field E oriented in the positive x direction in empty space. Find the net electric flux to the surface of a cube length L oriented as shown. So in this problem, we have a cube in the x, y, and z coordinate such that there is an electric field or uniform electric field passing through the positive x-axis. Okay? So positive x-axis meaning from here to here. So we have an electric field, uniform electric field passing through this cube in different directions. Okay, so let me just put it in our notepad. So let's go back here first. The image is much clearer here. So if the electric field passes through the positive x, what can you say about the electric flux at this surface with a normal vector dA sub 3? What can you say? Okay, if the electric field passes in the positive x direction and we're going to find the flux here, okay, on the top of the cube, top face of the cube, dA sub 3 or the normal vector A sub 3. So what is the flux there? The angle between the electric field, okay, the electric field, positive x, and the normal vector here is 90 degrees. So definitely, the electric flux here at the very top of the cube is 0. Why? Because the normal vector is in this direction, dA sub 3, and the electric field is in this direction. So 90 degrees, so that is cosine 90, that is equivalent to 0. The same at the bottom, okay? At the bottom of the cube, if the electric field is in this direction, the normal vector is facing here because it's always perpendicular to the plane, okay? The bottom plane, okay? The bottom face of the cube. So normal vector is here, electric field is here, so that the angle between the area vector and the electric field here is 90 degrees again. So that gives us a 0, what? 0 electric flux. Would you agree with me also that if we look at this if we look at this side of the cube, this side, okay? So there is a normal vector that is in this direction, okay? Because it faces the z direction. So would you agree with me that x, y, and z coordinate, what is the angle between the coordinates? X, y, for example, what's the angle? 90 degrees. If the normal vector of this side of the face of the cube is in the z direction and the electric field passes through the x direction, so the angle between the x and z direction or x axis and z axis is 90 degrees. So would you agree with me that the electric flux at this face of this cube is also 0? Yes, because it's 90 degrees. The angle is 90 degrees. And also on the back side of the cube, okay, where it traverses the negative z direction. Okay, so would you agree with me that there is an electric flux at this face of the cube? Yes. Why? Because the angle of the normal vector dA sub 2 and the angle between the dA sub 2 and the electric field is 0. So definitely, we have cosine 0 and that is equivalent to 1. Okay? And of course, would you agree also with me that the other side of the other face of the cube in this direction, this, okay, you can imagine this as this, okay, this dA sub 1, the face of that cube, its normal vector is facing against the negative x direction. Would you agree with me that there is an electric flux also there? Yes, because the angle between dA sub 1 and the electric field vector, which is traversing the positive x, and the normal vector traversing the negative x direction, that is a straight line. And the angle between them is 180. So what are we going to consider in calculating the total flux? Okay? The total flux in this cube is simply, since this is in terms of differential areas, differential area 2, differential area 1, we can use the integration definition of the electric field dot product between dA sub 1, okay, that is a vector, that product here, plus the integral of the electric field vector, the same electric field vector, product dA sub 2. Agree? Because this is our dA sub 1, dA sub 2. And again, plus 0, plus 0, plus 0, plus 0, because that would not make a difference, because plus 0 here, plus 0 here, plus 0 on this face, and on the back side, plus 0. Because the electric field and the normal vectors of the faces of the cube are perpendicular, so that is 0. So the only thing that is not perpendicular is the normal vector of dA sub 2 and normal vector of dA sub 1. So we have to compute that. Okay? And again, to get the total flux here, we have to integrate this. Okay? Can we actually translate it into magnitude? Yes, we can translate that into magnitude. So that should be the integral of the magnitude of the electric field multiplied by the differential area sub 1 cosine of theta. That came from the definition of the dot product. If we have two vectors A and B, and we're going to get the dot product of this, we can get the magnitude of A times the magnitude of B times cosine theta. This serves as our electric field, the A, and this serves as our differential area sub 1, which is this. Okay, so that from this dot product vectors, we get the magnitudes of this, plus the cosine theta, multiplied by cosine theta. Plus, of course, the integral, we can do the same here. So that should be electric field magnitude times the dA sub 2, the magnitude of the area vector sub 2, multiplied by cosine of theta. Okay? So, to analyze this carefully, we can say that the integral of E times dA sub 1 cosine theta. So, for A sub 1 here, okay, here is our vector. What is the angle of dA sub 1, or the normal vector of area 1 and the electric field? That is a straight line. So we have here dA sub 1 and the electric field is in this direction. Okay? So that the angle between them is 180 degrees. So we can get cosine 180 degrees, and that is equivalent to cosine 180 degrees. If I'm not mistaken, that is equivalent to negative 1. I'm correct. Okay? Plus the integral of E dA sub 2 cosine of the angle between the normal vector dA sub 2 and the electric field. As you can see from the figure, this is our dA sub 2, this is our electric field. So the angle, they are parallel. So the angle should be cosine of 0. And simply cosine 0 is 1. So simplifying our solution here, okay? So we can factor out E outside of the integral. Why? Because it's constant. We are concerned only for integrating dA sub 1. And we can also factor out negative 1 here. So negative 1 times E is negative E integral of dA sub 1. Okay? Plus, we have E times 1. That is simply E. That's constant. We can get it outside the integral sign dA sub 2. So now we have integral negative E integral of dA sub 1 plus E integral of dA sub 2. And what are we going to do if we're going to integrate dA sub 1? That's very easy. If we integrate dA sub 1, that should become A sub 1 plus E integral of dA sub 2. Okay, that should become A sub 2. Okay, but according to the problem, okay, what is this area? How are we going to evaluate the area? Okay, so we have the area here we are talking about is surface area. What is the surface area of a cube? The surface area of a cube, since they have the same length, okay, of each side, so the surface area of a cube is simply a square. And according to the problem, the sides of this cube is labeled as L. So if L is the side of the square, then getting the area of a square is L squared. So area of sub 1 is L squared. Since this is a cube, they have the same faces. They have the same square faces. So we can also say that our area 2 is simply L squared also. Okay, because the area of square is s squared. In this case, we have a length of L. So we have L squared. So negative EL squared plus L squared, that's correct. We get a zero flux in this cube. Okay? That's correct. Zero. Okay? We get a zero flux here inside or in the cube. Okay? So, here's the reason why. The reason why the electric flux is zero. Okay? The total net electric flux in this cube is zero. It's because the cube has no net charge inside it. I repeat, the cube has no net charge inside it. Okay? Because according to our lesson, later on, okay, we would be talking about Gauss's law, okay, which indicates that if we have a Gaussian surface, and inside that Gaussian surface, okay, imaginary surface, we have a charge inside. The electric flux in that surface is proportional to the total net electric charge inside that surface. Okay, so later on we're going to discuss that. So here is our solution for that. Okay, I hope you can follow. So yeah, our net electric flux in the cube is zero. So another example here, a positive point charge Q equals to negative 3.0 microcoulomb is surrounded by a sphere with a radius 0.2 meters centered on the charge. So meaning to say, we have a sphere, and inside the sphere, we have a positive point charge, which is Q is equals to 3.0 microcoulomb. Okay, inside the sphere, we have a charge. So, from what I've said a while ago, if we have a surface, and inside that surface, we have a charge, then definitely the electric flux is not zero because of Gauss's law. But in the cube a while ago, so we don't have any charges inside the cube. So we conclude that there is zero flux in that cube. Okay? So for now, find the electric flux through the sphere due to this charge. So we have here a sphere, and inside the sphere we have this positive charge which has 3.0 microcoulomb charge. And of course, what do we have if we have a single charge? We have an electric field that is pointing radially outward since this is a positive charge. Okay, so we have an electric field produced by this single point charge. Okay, would you agree with me? Here's the thing, okay? If a charge is enclosed in a sphere, the normal vector is always parallel to the electric field produced by that charge. So in this case, okay, at any point of this sphere, if we are going to get the normal vector, let's say in this piece of area, this is the normal vector dA, okay, and the electric field vector is denoted by red lines. Remember that this is in 3D, okay? Red lines or pink lines here. So the angle between them is zero since they are parallel to each other. So how do we compute the electric flux through the sphere due to this charge? So again, our formula is still the same. That is EA cosine of theta. Okay? So our electric field, the electric field is not given, but if you wish to recall, our electric field is produced by a single point charge is KQ over R squared. So we can get here what? The KQ over R squared multiplied by the surface area of the sphere. The surface area of the sphere is given by the formula 4 pi R squared cosine of theta. And again, cosine of theta, since theta is 0, since they are parallel, so simply we reduce our formula to simply KQ over R squared times 4 pi R squared. Okay, so what is this? We have 9 times 10 raised to 9 coulombs constant multiplied by Q, that is 3.0 microcoulomb, over what is the radius of the sphere? It is given 0.2 meters squared multiplied by 4 pi r squared. We have 4 pi r squared is 0.2 meters squared. So simply we can cancel out the 0.2 meters squared. Okay. So our calculation reduces to 4 pi times 9 times 10 raised to 9 times 3.0 microcoulomb. So 4 pi times 9 times 10 raised to 9 times 3.0 microcoulomb. And our answer, okay, our answer is what? Let's check. Our answer should be 3.4 times 10 raised to 5 Newton meter squared per coulomb. So 3.4 times 10 raised to 5 Newton meter squared per coulomb. As you can see here, our electric flux is not zero. Okay, because inside the sphere, we have a charge. Okay, and that's the concept of Gauss's law. Whenever we have a surface or a Gaussian surface, okay, the electric flux through that surface is always dependent on the total net charge inside that surface. Okay, so that is our next lesson here. So Gauss's law. So Gauss's law states that the total electric flux through any closed surface or Gaussian surface is proportional to the total net electric charge inside that surface. So if you don't have any charge inside the surface, then the electric flux is zero. Just like what I've shown you a while ago here in the cube. There may be an electric flux passing in the positive x direction, but if the closed surface do not have charge inside, okay, then the electric flux through that cube is zero. Okay. So Gauss's law. So for example, here is Gauss's law, Carl Friedrich Gauss. So he's also a mathematician. Okay. So we're going now to derive the Gauss's law. Okay. So for example, we have this figure. Okay. So the field lines, as I've said a while ago, are directed radially outward. Okay, because this is a positive charge, and hence perpendicular to the surface at every point on the surface. So the electric field, okay, produced by the single charge inside the spherical surface, again, is always perpendicular at any point surface delta sub A, okay, normal vector. It's always parallel to the electric field, so that the theta becomes zero. So in order for us to derive the Gauss's law, okay, so we have the formula that the flux inside the surface is simply equal again to the integral of the electric field vector dotted by dA. Okay, so we're going to make that as these are two vectors. We're going to make that as magnitude. So we have EA cosine of theta, EDA cosine of theta. So cosine of theta, since this is a sphere, is always the angle between the electric field and the normal vector on any point on the sphere is, again, what I've said is 0. So they are parallel. So cosine 0 is simply 1. So we are left with E integral of dA. And we can get that. Okay. So integral of dA is simply EA. Okay. Again, here's our flux. Simply EA. Okay. But what is the electric field produced? Okay. What is the electric field produced by a single point charge? So we have KQ over R squared. And the surface area of the sphere, again, is 4 pi R squared. So we can see here that R squared will cancel. We are left with 4 pi KQ. Okay. So what is K? That's correct. That is equal to 9 times 10 raised to 9. But what do I mean by K? If you haven't watched my videos, K is Coulomb's constant. And that is also equal to 1 over 4 pi epsilon sub 0, where epsilon sub 0 is the permittivity of free space. So, substituting K as this, so we have 4 pi Q multiplied by K, which is 1 over 4 pi epsilon sub 0. So, as you can see here, 4 pi's will cancel. And we are left with the electric flux as Q over epsilon sub 0. And this is now our, what we call the Gauss's law. And it states that the electric flux inside any closed surface or through any closed surface is proportional to the total net electric charge. Okay, total net electric charge. Okay, so this is now our Gauss's law. So the formula is pretty simple. Q over epsilon sub 0. So the value of epsilon sub 0 is 8.854 times 10 raised to negative 12 farads per meter. Let me just write here in case you forgot. So the permittivity of free space is 8.854 times 10 raised to negative 12 farads per meter. Okay? The units are not important anyway in this subject, so you have to memorize this. Or if you are using Casio FX991ES model, you can input this as by inputting shift constant 32. Okay, so let's try again. So now consider several closed surfaces surrounding a charge Q as shown in the figure. So for example, in our first figure class, we have a sphere. Okay, and inside this sphere is Q, positive test charge Q. Now, we also have an irregular shaped surface and we call that surface 2. And also, we have an irregular shaped surface, we call that surface 3. So, my question is the flux in surface 1, which is a sphere, the same as the flux in the surface 2 and the same as the flux in the surface 3? Do they have the same flux? Yes, because they are enclosing the same charge. Okay? So, the net flux through any closed surface surrounding a point charge is given by the formula Q is over epsilon sub 0 and is independent of the shape of the surface. So, what we can derive here is that if we have a point charge, no matter what shape it is enclosed, as long as there is charge inside that surface or closed surface, then the net flux is equal to Q, whatever value of that charge, divided by the permittivity of free space. Okay? It is not dependent on the shape. So meaning, whatever shape it is, it may be a cube, it may be a circle or sphere, it may be an irregular shape. As long as that closed surface encloses a charge, so our value for the electric flux is always Q over epsilon sub 0. Okay? A point charge located outside the closed surface, the number of lines entering the surface equals the number of lines leaving the surface, of course. So, for example, here we have a charge. It's producing an electric field. Okay? So that its electric field passes through this closed surface. Okay, and it says that the number of field lines entering is equal to the number of field lines leaving the surface. So my question is, if I'm going to ask you, what is the electric flux through this closed surface? What is the electric flux? Remember, okay, we don't have any charge inside the surface, even though we have a charge outside the surface and it's contributing to the electric field experienced by this closed surface. So, what is the electric flux inside this surface? Yes, that is 0. That should be 0 because there is no charge inside. And if there is no charge inside, again, Gauss's law states that the electric flux through a closed surface is always equal or directly proportional to the total net electric charge inside that surface, surrounding that surface. Okay? So, closed surface. So, if we don't have any charge, then 0 over epsilon sub 0 will be 0. Okay? So, there is no charge inside the cube on our previous example, even though there is an electric field passing through the cube. But as long as there is no charge inside the cube, the electric flux through the cube is 0. The same for this closed surface. Okay, I hope you can follow. So Gauss's law, this is only the what do you call this? The sum. Okay, if you have different electric fields, so this is not really important. Okay, but it's worth taking note that if we have different electric fields, we can sum up all the electric fields in vector sum, then get the electric flux. Okay, so the net electric flux through any closed surface depends only on the charge inside that surface. Again, that is Gauss's law. Suppose that we have three surfaces. So we have S surface here, we have S prime surface here, and we have S double prime surface here. Okay, quick question. What is the electric flux at surface S? That is actually Q sub 1 over epsilon sub 0. Why? Because this surface surrounds Q sub 1. And inside the surface, we have Q sub 1. So our electric flux is Q sub 1 over epsilon sub 0. How about S prime? How about S prime? This surface. So, that's correct. The net flux through S prime, okay, surface S prime is Q sub 2 plus Q sub 3. Oops, forgive me for this. This should be Q sub 2 plus Q sub 3 over epsilon sub 0. Sir, how is it if we have two charges that are opposite in sign? For example, this is positive, this is negative. Well, consider getting the what? Still the sum. So if this is 1 microcoulomb, positive 1 microcoulomb, so that is a positive charge. If this is negative 2 microcoulomb, okay? So positive 1 microcoulomb minus 2. So 1 minus 2 microcoulomb is negative 1 microcoulomb. So your flux should be negative 1 microcoulomb over epsilon sub 0. So that's how you get the electric flux if we have a given value charge. Okay? So the net flux through surface S double prime, again, since it encloses no charge, again is 0. And I hope that's clear with you. Okay? So the charge 4 does not contribute to the flux through any surface because it is outside all of the surface. Agree? So if we have many charges here, as long as the charges are not inside this closed surface, it would not affect the electric flux inside S prime, and S double prime. Okay? What only affects the electric flux to any closed surface is, again, the net electric charge inside the surface. So we have spherical Gaussian surfaces, just like what I've said a while ago. If you have a positive charge here, single point charge, our electric flux is simply Q over epsilon sub 0. If we have a negative charge inside this surface, so what will happen? We simply have negative Q over epsilon sub 0. In this problem, we're going to consider the signs of the charges inside the surface. So if you have a positive charge, okay, so we have an outward flux. If I have a negative charge, well, of course, the electric field's direction is inside towards the charge. So we have an inward flux for a negative point charge. So to test your knowledge again, okay, let's try to solve some problem. A spherical Gaussian surface surrounds a point charge Q. So we have a surface that surrounds a point charge Q, meaning the magnitude of Q can be, let's say, positive 1 microcoulomb, 1 picocoulomb, etc., etc. So we have a spherical Gaussian surface surrounding a point charge Q. Describe what happens to the total flux through the surface if, letter A, the charge is triple. So what will happen? What will happen to the flux if the charge is triple? So what will happen? Okay, if the charge is tripled, according to Gauss's law, flux in any closed surface is equal to Q over epsilon sub 0. So this is our original flux. Okay, so what will happen to the flux sub 1? Let's say if we triple, okay, the charge. So since we are tripling the magnitude of the charge, this flux would also triple because it is directly proportional to the magnitude of the charge. So our answer for letter A is the flux would also be triple. Okay? So for letter B, the radius of the sphere is double. So we have here a sphere, let's say, and inside this we have a positive charge. Okay, forgive me for my drawing. So this has a radius r. Okay, if we are going to what? This is our surface sub 1. Okay, s prime. Let's say this is our surface sub 2. So we double now the radius. Okay, what would be the effect on the flux? What would be the effect? Nothing. That's correct. Nothing. Because flux is not dependent on the radius, okay, through which it is placed inside the sphere. It's not actually dependent. Even on the shape. Okay? So, it is only dependent on the total net electric charge as given by this formula. So, nothing will change. Letter C, the surface is changed to a cube. From a sphere, it is changed to a cube. What will happen? Again, nothing will happen. Okay? Okay, nothing will happen. It is independent on the shape of the cube, of the surface, closed surface. Okay? So for letter D, the charge is moved to another location inside the surface. So as long as the charge is inside the surface, okay, we have a flux. So as long as also that we move it to another location, what will happen inside the surface? As long as it is inside, nothing will happen to the flux. As long as the charge is inside. Once you remove it inside the closed surface, then the flux will change eventually. Okay? But since it is only moved in another location inside the surface, okay? So if we have a surface here, let's say this is our surface, okay, this is my charge. If I'm going to move it here, nothing will happen. If I'm going to move it here, nothing will happen. The charge is still the same, or the electric flux is still the same. Q over epsilon sub 0. Nothing will happen. Okay? So here is our answer. It is independent, or regardless, or independent on the location inside the surface. Okay, application of Gauss's law to various charge distribution. Well, of course, there are some conditions wherein we can use the Gauss's law. So for number 1, the value of the electric field can be argued by symmetry to be constant over the portion of the surface. So in other words, if the electric field is constant over the portion of the surface, okay, we can use the Gauss's law. Number 2, the dot product of the closed surface integral of electric field vector E and normal vector area dA can be expressed as a simple algebraic product EDA because E and dA are parallel. So in other words, if the cosine or the theta is 0, okay, we can apply the Gauss's law there. And of course, if also the dot product of the equation E dot dA is 0, because E and dA are perpendicular. In other words, if the angle is 90 degrees or perpendicular, then we can also use the Gauss's law. And the electric field, if the electric field is 0 over the portion of the surface. So, the Gauss's law is also helpful in determining electric fields of some of the charges. Okay? So, in this example, an insulating solid sphere of a radius has a unit A, okay? This is the solid sphere. Inside that solid sphere is Q, okay? A uniform volume charge density and core carries a total positive charge Q. Calculate the magnitude of the electric field at a point outside the sphere. So this is the where we are going to calculate the electric field here. So as I said a while ago, that Gauss's law is useful in determining electric fields. So how are we going to get the electric field of that problem? Okay. So here, okay. So from our definition of electric flux, again, that is EA, okay, EA cosine of theta. And inside a sphere, thus, we can use what? The Gauss's law. Because the electric field vector produced by the single charge inside the sphere is always parallel to the normal vector of at any point surface of the sphere. So we satisfy one condition in order for us to use the Gauss's law. So The flux also is also equal to what? The Gauss's law. By Gauss's law, that is Q over epsilon sub 0. Okay. And what are we going to do is to get the electric field at this point in space outside the closed surface. So, if this is phi is equals to phi, we can actually what? Have this as Q over epsilon sub 0. Okay? That should be equal to EA cosine of theta. Well, actually, our flux should start with the integral of E and dotted by dA, E vector. So, simply, we can get naman yan as EA then. Okay? So, what are we going to do? Simply, what? So, we have here Q over epsilon sub 0. We can get since this is cosine of theta is, the theta here for E sphere is, again, what? 0 degrees. So, if that is cosine 0, that is 1. So, our formula is reduced as E times A Q over epsilon sub 0. So, we can get the electric field. The electric field is, at that point, is simply, what? Q over epsilon sub 0 A, or Q over, what is the surface area for a sphere? That's correct. That is 4 pi r squared epsilon sub 0. And this we can get the electric field at this point using Gauss's law. Okay. So, for our last example, so find the electric field at distance r from a line of positive charge infinite length and constant charge per unit length lambda. For example, we have a line of charges, positive charges here, a line of positive charges here, and we're going to create a Gaussian surface which is in the form of cylinder, okay, with the length L, and of course, we're going to get what is the electric field at this point due to the positive line of charges. So, let me see if I've copy-pasted here our example, okay? So, what are we going to do? Okay, and again, from the definition of electric flux, that is EA cosine of theta. And as you can see here, the theta at any point in the cylindrical surface, Gaussian surface, since electric field is here, then the normal vector is also here, then we can say that they are parallel, so that their angle is equal to 0. And again, this should be cosine 0, and that is simply equal to 1. So we have the flux equal to EA. And we can use Gauss's law also here as flux over is equal to Q over epsilon sub 0. The line of charge, Q. Okay? We can represent that as simply Q, or inside the surface, Q in. Okay? We can use also Q in, or simply Q. Okay, so there is what we call the problem, we have here the positive charge infinite length and constant charge per unit length lambda. So lambda is what? Constant charge per unit length, or we can say that that is Q over L. Okay, in order for us to use this constant charge per unit length lambda, this is lambda, Greek alphabet lambda, what are we going to do is, we're going to simply substitute it here in our Q here. So it turns out that what are we going to do if we multiply, okay, if we multiply this flux both by L, okay, and substitute this lambda here. So what will happen? We will be having lambda, okay, multiplied by L over epsilon sub 0. Why does that happen? Why did it happen? So lambda is charge per unit length. So in other words, charge per unit length multiplied by epsilon sub 0, and this is length. Okay? What will happen is, it turns out that if we have this equation, it's the same as Q over epsilon sub 0. Why? Because the L's will simply cancel out here. Okay, if we have the lambda times L here over epsilon sub 0. Okay, that's it. So again, equating the two equations, we have EA is equals to lambda times L over epsilon sub 0. So getting the electric field, so we have E is equals to lambda over times L over A multiplied by epsilon sub 0. And the surface area for a cylinder is we have a length of L, height of L, so the surface area should be 2 pi RL. So we have lambda L over 2 pi RL multiplied by epsilon sub 0. So the L's will cancel here. We have lambda over 2 pi R epsilon sub 0. So that must be the electric field at any point. Diba? Okay? With an R distance from the positive line of charge. Okay? So, here are our references: University Physics by Young and Friedman and by Survey, University Physics for Engineers. So that's all. Thank you for listening and God bless you. That is Gauss's Law and electric flux. See you on the next video.